Hi everyone, my name is Annie Joben and today I will be presenting on the application of linked list for student registration systems. We will look at how this data structure manages student data effectively, specifically focusing on the logic behind inserting new registrations into the middle of a list. Efficiency is the key in managing student registration. In this presentation, we will explore how linked lists maintain the registration order. A major challenge in registration is handling mid-position insertion, such as when a priority student needs to be placed between the others. We will see how linked lists ensure both fairness and efficiency during this process. Consider a typical college course registration system where students are registered in the order they apply. However, reality is rarely a perfect line. We often have late applicants or transfer students who must be inserted between existing students based on specific priorities. Because of this, the system must be flexible enough to support middle insertion without breaking the existing registration order. So, why use a linked list? Managing registrations dynamically requires a flexible data structure. Traditional arrays are inefficient when you have to insert items frequently because they require shifting every subsequent element. Linked lists, however, facilitate easy mid-position insertions. This ensures the order is maintained seamlessly even during frequent updates. Let's look at the structure. A singly linked list is made of nodes. Each node contains two things, the student's data and a pointer that directs us to the next node in the sequence. This design allows for dynamic memory allocation, meaning the list grows as we add students and makes insertions very efficient. It's a perfect fit for maintaining a seamless registration order. So, how do we perform a middle insertion? It follows four clear steps. First, we create a new node containing the student's data. Second, we traverse the list starting from the head until we reach the node just before where we want the new student to be. Third, we update our new node's pointer to point to the current node's next. Finally, we update the current node's pointer to point to our new node. This links the new student into the chain. If we look at the pseudocode for insert middle, you can see the logic in action. If the position is 1, we simply make the new node the head. For middle positions, we use a temporary pointer called temp to walk through the list. We loop from the start to the position right before our target. Once there, we adjust the pointers. New node, next, take over, temp next. And temp next is updated to point to our new node. This effectively slots the student into the list. Let's walk through a visual example. Imagine we have a list of students A, B, C, and D. We want to insert a new student X at position 3. We initialize our temp pointer at student A. We calculate our loop range as position -2, which in this case equals 1. This tells the system how many steps to take to find the correct insertion point. As we move temp, it stops at student B before the link B pointed directly to C. After we update the pointers, B now points to our new student X and X points to C. Our final registration order becomes A, B, X, C, and D. We have successfully added a student to the middle without moving A, B, C, or D in memory. From a technical standpoint, the time complexity for mid-position insertion is big O of n because we may have to traverse the list to find the spot. The space complexity is also big O of n as it scales linearly with the number of students added. While arrays have a fixed size and struggle with shifting elements, linked list handles these dynamic actions with much more gracefully. To summarize, why we choose this over an array. Arrays are a fixed size and require costly element shifting during insertion. In contrast, linked lists are dynamic. They grow and shrink as needed. There is no shifting required, only pointer updates. This makes them ideal for frequently changing data, such as a live student registration list. In conclusion, linked lists provide an efficient way to handle dynamic student registrations. Middle insertions are made simple and fast through pointer updates rather than data shifting. This ensures the correct registration order is maintained with minimal memory waste. Thank you.